because now the threefold symmetry is not along a given axis, but the threefold symmetry you see here is along the diagonal, and this you must bear in mind, because when you talk about the point group symmetries you will have to worry about these. Now, let us come back to the trigonal symmetry which we were discussing. So, the trigonal symmetry therefore must have is represented with the z direction to have the threefold symmetry. So, the other two symmetries which can occur in this particular case are either along this given x direction or along the 120 degree angles, because there is a threefold symmetry. The threefold symmetry can take this point to that point to that point, and also it can take this point to that point and that point. So, 120 degree rotations on either side with a twofold symmetry will be representing the 3-2-2 symmetry, for example. So, what we consider here is only the 3 symmetry. So, that means there is no symmetry associated with x and y directions. Now, how will you represent a trigonal system in terms of the ABC? The trigonal system is represented in terms of ABC. It is actually a similar representation to the hexagonal system, and the values of A, B and C and alpha, beta, gamma will be represented slightly differently, and how differently it is represented we will discuss later when we go to the discussion on the crystal system, the Bravais lattices and the assignment of the space group. So, at this moment we just consider the operation of a threefold symmetry on an object. The object now is representing a threefold symmetry. So, that means the object is located here, represented here, it rotates by 120 degrees. No, I am on the wrong one. This object rotates by 120 degrees and again rotates by 120 and again rotates by 120 and comes back to the same position, and therefore, this is a point group symmetry 3. There are no additional symmetry elements. So, there are 3 equivalent points here, and in this particular situation there is no special position either, because we do not invoke any possibility of a special position. On the other hand, if we have a 3M system as is shown here, where you see that this point which is x, y, z now rotates by 120 degrees, goes to that point and rotates again by 120 degrees and comes to this point. The second symmetry that is operating is an improper symmetry. So, when the first is a proper symmetry, the second one is an improper symmetry, what should be the third one? The third one should be also either a proper or an improper rotation. So, which is the one which is possible? So, if there is a proper rotation and then an improper rotation, the third one has to be improper. So, that means there is also a mirror symmetry in the third direction. So, these twofold axes which are shown here in 3-2-2 case now will become 3 mm. In fact, it is 3 mm. We write it as 3m for simple purposes, because we know that the other mirror will automatically appear. There is no possibility of any other symmetry to appear other than the mirror symmetry, and that is why you see that each one of them is related by a mirror symmetry. So, we generate 6 equivalent points. Now, what happens to if the object is sitting on a mirror in any of these positions? Then the object will mirror reflect onto itself, and therefore, there is a possibility of special positions which can come in this particular point group symmetry. The next symmetry is the operation where we have a threefold symmetry followed by an inversion. So, there is an inversion which is associated with the threefold symmetry, and both of them are along the same axis. That means, this is the axis which is 3 now, it becomes 3 bar. It carries the inversion operation along with it, and therefore, it again generates 6 equivalent positions in the projection diagram, in the stereographic projection. The threefold symmetry will generate these 3 x's, and then the corresponding inversions occur, and so we generate these 3 open circles. So, if this is x, y, z, will you get an x bar, y bar, z bar in a 3 bar symmetry? This could be taken as an assignment. In fact, probably it will appear in the assignment sheet. So, what is 3 bar? 3 bar is different from 2 bar. See, in case of a 2 bar, we have a two-fold rotation followed by an inversion, and the two-fold, it is not even followed by an inversion, the two-fold itself inverts. The option for the two-fold itself to invert is given because it is 180 degree rotation. In a three-fold symmetry, we have a 120 degree rotation. So, the inversion about 120 degrees itself is not activated if you have a 3 followed by 1 bar. 1 bar can take only x y z to x bar y bar z bar. So, if this is at 1/3 position, then going to minus 1/3 and minus 2/3 is not going to put them on top of each other. So, 2 bar degenerates to mirror, whereas 3 bar will be actually an operation 3 followed by 1 bar. So, 3 followed by 1 bar is not going to generate any mirror symmetry, and therefore, this becomes an independent point group, and this particular point group has 6 equivalent points. So, the trigonal system therefore is now described with respect to the possibility of having one single axis in these three diagrams, in these two diagrams 3 and 3 bar. 3M is a situation where it can have the presence of two-fold axis as is shown here, or it could be 2 mirrors, and what is shown here is the presence of 2 mirrors. So, it is a proper improper rotation which essentially generates again 6 equivalent points. You see that the mirror planes are now 3 of them associated with each 3-fold rotation. So, that means they are mutually perpendicular to each other, the mirror operations, as is seen here. So, there is a mirror operation up here, the mirror operation there, mirror operation there instead of the 2-fold, and therefore, you indicate all those 3 in these 3 dark lines, the dark lines representing the mirror operation. So, we will go further on the trigonal system. The next trigonal problem will come up because of the following. Let me erase this unnecessary stuff here. So, you see here 2 space groups which are now containing operations. What is bothering you at this moment, I am sure, is that where is the third axis. So, you are saying there is a 3 bar, you earlier said 3 bar is a 3-fold and a 1 bar operation, and then there is a 2 by m. There must be one more operation. Now, the 2 by m operation is also a center of symmetric operation. 2 by m by itself is a center of symmetric operation. Now, that center of symmetry comes up there. So, you have a 3-fold, along with that a center of symmetry. So, the presence of the 3-fold and the center of symmetry takes this particular fellow, well, it rotates, let us take this one, it rotates by 120, again 270 and then comes back, that is the 3-fold, and the corresponding inversion axis will take them to these open circles. They are also related to each other by an inversion. So, therefore, we have 3 bar and 2m generated automatically. So, what would be, you think, would be the next direction? See, you have 3 directions in a hexagonal system. Let me go back to the previous slide. In this slide, you see that we have a 3-fold rotation, okay, and then you have 2-fold rotation axes which are at 120 degrees to each other, and they are intersecting with each other at this center here. The 3-fold rotation is the one which has generated these axes, and then we can associate with these axes, either we can associate a rotation axis or just leave it as such. If we leave it as such, we get the 3-fold rotation or the 3 bar rotation. If we do not leave it as such, we can have option of a 2-fold and a 2-fold, which means we have 2 proper axes. Now, if we have 2 proper axes and a 3-fold rotation, is it possible to have a space group? Is it possible to have a point group? That is possible here in the one which is shown below. So, this shows 3-fold along the z direction, 2-fold in a direction which is x, and that is enough because the third direction will automatically get defined, and that third direction will have to be a proper axis, and in this particular case this has to be an improper axis. So, you will have effectively a mirror here and a 2-fold here, and in order to represent that in a simpler manner, the accepted representation of point group symmetries are 3 bar 2m and 3 2. So, here in fact the full symmetry associated with this will be 3 bar 2 by m and m, and in this case it is 3 2 2. So, the moment you have a combination of a proper and an improper axis, the third axis will be automatically improper. Whereas, if you have two proper axes and one remaining improper is not possible, and therefore, you will have proper axis. So, it will be 3 2 2 and 3 bar 2 m m. Those are the actual representation of full symmetry, and that is not necessary to describe. So, we just say it is 3 bar 2 by m, and in this case it is 3 2. So, these two trigonal systems therefore, now will define a set of equivalent points. In this particular case, you see 1 2 3 4 5 6 7 8 9 10. So, there are 10 equivalent points, and this is interesting because what will happen when it is put in a 3-dimensional lattice? In other words, what will happen to this point group symmetry when we describe it with respect to a lattice? This question you keep thinking about. We will discuss it when we describe the space group associated with the trigonal symmetries. Trigonal symmetry therefore, is always a very interesting system, and not many molecules go into this trigonal symmetry, and if they do go into the trigonal symmetry, there will be some very interesting properties which will develop. So, we will just keep that in mind and we go further to the tetragonal system. Tetragonal system is a little simpler system than the trigonal system from the point of view of understanding. So, we will make an attempt to understand the tetragonal system. How do we define a tetragonal system? We define a tetragonal system the following way. We say that in a tetragonal system, A is equal to B, not equal to C, alpha, beta and gamma are at 90 degrees. So, A equals B, not equal to C. So, it is the C direction again which is unique. Just like in the trigonal system, the 3-fold symmetry was the unique axis. The 4-fold symmetry is the unique axis for this system. And therefore, you see that if you have just the presence of a 4-fold symmetry and no other symmetry intersecting with each other, then you have a 4-fold symmetry which will generate 4 equivalent points. These equivalent points get generated at 90 degrees with respect to each other. What is important to notice here is that since A is equal to B, they are degenerate. So, you can call A as B or B or A, it does not matter, because A equals B defines a square planar lattice, and that square planar lattice will be associated with a 90 degree angle. It so happens that the C direction, which is now coming perpendicular to this square lattice, the value of the value C will now decide that it is going away from a cube, because in the case of a cube, A equals B equals C. So, now this C lattice, the presence of C which is different from A and B, tells us that we take a cube and pull it out. It is a stretched cube in the direction of the z axis. That is what is shown here. You see that the 4-fold is stretching out away from the axis. So, this is the point of intersection. So, at the point of intersection, we can still invoke the presence of other axes, but the point group symmetry can exist as itself as 4, and therefore, we can invoke 4 bar, which is associated with a center of symmetry. Now, what do you think are the equivalent points in 4 bar? I have left this equivalent point positions unattended or unmarked. So, these equivalent points therefore, will now bring in a separate concept altogether. So, I want you to take it as a home assignment and mark the equivalent points for 4 bar. 4 by m symmetry, which is a simultaneous existence of 4 along with a mirror, will create a center of symmetry. These two are non-center symmetric. There is no center of symmetry that is involved in this. These are non-center symmetric, and therefore, you have now 1 2 3 4 and the corresponding 4-fold rotation as well as the mirror symmetry inside this. So, you will have 8 equivalent points here. You have 4 equivalent points there, 4 equivalent points here, and 8 equivalent points there. So, what it means is that if we take the value of z, the value of z now varies considerably. So, if you have a molecule which can be put into a tetragonal system, obviously, the presence of the 4-fold system will invoke the presence of more than one molecule, and in fact, it will be more than 1, in fact, it is 4 or 8 or even higher. So, depending upon the nature of the crystal system, therefore, the molecules which will now go into these higher symmetry systems, this can be considered a higher symmetry crystal system, the number of molecules can increase. But what is interesting to remember and note, it is just a note at this particular point, is that when we are now dealing with tetragonal systems, as I already mentioned, most of the tetragonal systems are inorganic rather than organic. And the reason is that the tetragonal system now can accommodate and invoke the presence of possibility of 90-degree rotation. So, the molecule therefore can go 90 degrees, another 90 degrees and further 90 degrees before it can come and overlap. So, the symmetry like the trigonal, tetrahedral and octahedral geometries are most suited for molecules to go into the tetragonal system. So, if the system does not go into a cubic system, the inorganic systems prefer the tetragonal symmetry. So, if you look into literature, you will see a very large number of tetragonal systems which take the octahedral, tetrahedral molecules into them, and that is something which we should note, because tetragonal symmetry occurs very often in inorganic systems. So, the presence of the 4-fold, the 4-bar symmetry and 4/m symmetry, the point group symmetries are shown here, the equivalent points are generated, and as I said, the assignment will be for you to generate the equivalent points of 4-bar. Apart from that, since A is equal to B and not equal to C, the number of types of lattices as a consequence will reduce. It will be now only a primitive lattice and a body centered lattice. Only these two are possible in a tetragonal symmetry. We are going to prove this later on when we discuss the possible Bravais lattices that can be associated with crystal systems. Even though we have listed it out in the previous classes, the detailed analysis of why only P and I are possible will be done in the coming classes. So, please notice that as far as the tetragonal system is concerned, there is no question of having a F centered lattice or A, B, C centered lattice, because of the fact that the geometry sort of forbids any other lattice that can exist other than primitive and I centered lattice. So, the number of space groups associated with the tetragonal as a consequence will reduce to that extent. However, the number of point groups that are associated with the 4-fold system increase, and so we get a very large number of systems that are possible. So, for example, in this particular illustration, you see that we have now the possibility of the 4-fold rotation along with the possible perpendicular rotations associated with the 4-fold rotation. That means, the 4-fold rotation can go 90 degree, 90 degree and another 90 degree. So, the total number of possible symmetry elements are indicated here. So, 4 can go with a 2-fold as well as a 2-fold. That means, 4 can go with a mirror and a mirror. So, we have to consider all combinations of proper, improper and proper axis combinations, and so we get additional point group symmetries, which is 4-bar 2m and 4-2-2. Again, in this particular case, we have illustrated the equivalent point positions of the 4-2-2. You see that this is the 4-fold position, and this 4-fold position will generate 4 of these equivalent points, and with the operation of the 2-fold, which is now associated in a direction of 90 degrees with respect to each other. As you see that there is an axis which will go like that, which is a 2-fold axis, a perpendicular axis like this, and then 2 diagonal 2-fold axis which can go with the 4-fold symmetry. Let me show it again clearly. You have an axis going like that, an axis coming like that, and both these are 2-fold axes. Perpendicular to that are the 2 axes which go along the diagonals. This is a 2-fold axis and that is a 2-fold axis. So, because of that, we will end up with the 8 equivalent points that are associated with 4-2-2. 4-bar 2m now will have additional mirror symmetries which now go along the diagonal. We have the 4-fold symmetry, and then in addition we also have the 2-fold symmetry which will get embedded with respect to this. So, the last m is actually 2/m. So, we will also have a 2-fold symmetry at the center of it. So, tetragonal systems therefore are defined with respect to the presence of the 4-fold axis and the various possible 2-fold symmetries that can be associated with the 4-fold axis. The 4-fold axis again in general is representing along considered along the z axis, just like the trigonal axis where we consider the threefold along the z axis. The same story goes with the hexagonal lattice as well, which is 6 2 2. We will go to the hexagonal system now after showing the remaining part of the fourfold rotation. So, we can have the 4 for this 4 mm is there, and we also have the 4 by m, 2 by m, 2 by m. Both these systems, point group systems, will generate in one case it is 8 equivalent points, in the other case 16 equivalent points. Along with the possibility of these now going into more than one type of lattice, that means they can go both into the primitive lattice as well as, let me write it down, it can go and into the primitive lattice as well as eye centered lattice. So, the moment we have an eye centered lattice for every x, y, z, every coordinates which we generate, of course, every equivalent point which gets generated by the p lattice operation, you have to add half plus x, half plus along x, half plus along y, and half plus along z. So, for every x, y, z, we have to add a half plus, half plus, half plus in order to take it to the eye center. So, if there are 8 equivalent points in this 4 mm, if we now take it to the eye system where the eye centering is introduced, you will have another 8 additional equivalent points, and therefore, there will be 16 equivalent points. What it essentially means is that you, as I mentioned already, you can pack 16 molecules. But what is also interesting at the same time is that when we really crystallize the inorganic systems particularly, because of the presence of the tetragonal symmetry and the octahedral symmetry, these symmetry elements can adjust themselves across the fourfold symmetry. And because they adjust across the fourfold symmetry, the number of molecules will reduce considerably. In other words, the molecules or the molecules which go into these kind of systems generally utilize the fourfold special positions. The special positions which are offered in these crystal systems will be utilized, and as a consequence the number of molecules in the unit cell will anyway reduce. So, as we go to higher crystal systems, as I mentioned already, the number of equivalent points will increase. In fact, when we go to the cubic system, there will be 192 equivalent points. But when you crystallize systems into these, only highly symmetric systems crystallize, and that is the reason why organics prefer only the triclinic, monoclinic, and orthorhombic systems. And here the inorganic systems tend to crystallize. And therefore, if one thinks of the recent organic inorganic hybrids, for example, the hybrid structures can go into higher symmetry space groups, because they maintain the inorganic symmetry, inorganic crystal symmetry intact, and then incorporate the organic molecules, so that the organic molecules now are forced to obey these symmetries, and therefore, the property of the organic system therefore can be controlled. And this is how the metal organic framework structures and the covalent organic framework structures and so on, the MOFs and the COFs and all that are becoming more and more exciting, because they are put in a highly symmetric atmosphere, and therefore, they are constrained in their conformational flexibility. As a consequence, some special reactions can be carried out inside these moieties, and that is how these compounds become extremely important. This is just a side point I thought I will mention. Now, we will go to the hexagonal system. Again, in the hexagonal system, you see that the 6-fold symmetry is now perpendicular to the direction. In fact, this is a 6-fold symmetry. It looks like a 2-fold in this diagram, but it is a 6-fold symmetry, and 6-fold by itself can exist just like the 3-fold and the 4-fold. So, we get the 6 bar and 6 by m, and in this particular case the equivalent points appear at 60-degree rotations, because it is a hexagonal symmetry, and in fact the value of A, B and C will be A equals B not equal to C, alpha equals beta, alpha equals beta equals 90 degrees, and gamma is 120 degree. Gamma is 120 degrees. So, this kind of a relationship exists for a hexagonal system, and we have therefore 6 points which will be generated by a 6-fold symmetry. 6 bar generates, you see, also 6 points, one above and one below each other, because you see here there is a 6-fold and then a 3-fold incorporated into that. This is what I discussed when I actually initially talked about the 32 point group symmetries. I told you to find out the difference between the 6 bar symmetry and the 3 bar symmetry. The 3 bar symmetry has 6 possibilities. Here also there are 6 possibilities, but in the 6 bar symmetry, because of the higher symmetry nature associated with a 60-degree rotation, in the case of the 3-fold rotation, it is a 120-degree rotation. You will generate 6 points there, whereas here you generate the 3 points up and 3 points down. Effectively, again here the 6 points are generated, but they are one on top and one on the bottom. The 6 by M symmetry generates again a mirror symmetry, which is now attached along with this, and you now see because of the fact that there is a mirror symmetry which is perpendicular to the 6-fold symmetry, you will get now 6 equivalent points and 6 below. So, the hexagonal symmetry therefore is again representable in terms of the other intersecting axes. So, we have additional point group symmetries 6 bar M2, 6 mm, and the equivalent points are marked here. Then we additionally have 6 to 2, 6 by M, 2 by M, 2 by M. This is the highest symmetry that can be taken up by a hexagonal system. What happens to the hexagonal symmetry with respect to the lattice? It has only one type of lattice, in fact that is a primitive lattice. So, we only have a primitive lattice, and the presence of the primitive lattice therefore is only invoked in a hexagonal system. There is no other possibility. And so, even though the number of point groups, as we discussed in case of the tetragonal system, are more, the number of lattices we can generate with hexagonal symmetry are less. And this now is coming is going to help out to find out why only 230 space groups exist. So, we have only primitive lattice in the hexagonal system, and as I was telling you that there are 230 space groups as a consequence. So, the number of space groups are limited to 230, and I do not know whether it develops some static or something. So, the 6-fold symmetries therefore get defined. The presence of the 6-fold symmetry now generates these many point group symmetries 6, 6 bar, 6 by M, 6 bar M2, 6 mm, 6 to 2, and 6 by M, 2 by M, 2 by M.